afternoon, children. Did you have your lunch? Okay, now we will pass on our chemistry live class. Okay, and in the morning class you studied about the zeroth law of thermodynamics, first law of thermodynamics and its various statements, then enthalpy, that is H, and the relation between enthalpy and the internal energy, and some of the thermochemical equations. Okay, now we are going to see molar heat capacity, that is molar heat of combination, molar heat of formation, molar heat of neutralization, like that. Then we are going to calculate the delta U, that is internal energy, by using bomb calorimeter, and then we will pass on the delta H measurements. Okay, then after that we are going to read about the Hess's law and its applications. Okay, now we will pass again the same heading, molar heat capacities in detail.
Okay, we will see the molar capacity now. When heat is supplied to a system, the molecules in the system absorb heat and hence their kinetic energy increases, which in turn raises the temperature of the system from T1 to T2. This increase, that is a T2, the difference in the temperature, T2 minus T1 in temperature, is directly proportional to the amount of heat absorbed and the mass of the substance. In other words, Q, that is a heat capacity, is directly proportional to M into delta T. Here M is the mass and delta T is the temperature difference in Kelvin. Q is equal to Cm delta T. Here C is called as the constant, proportionality constant. If you are considering only C is equal to Q, taking the other things to the opposite side, then you will get Q by M into delta T. The constant C is called the heat capacity. That is C is equal to Q by M into T2 minus T1, that is delta T. When M is equal to 1, that is mass is equal to 1 kg and the temperature difference is 1 Kelvin, T2 minus T1 is 1 Kelvin, then the heat capacity is referred as per the equation. M also 1 and T also 1, so the denominator entirely becomes 1, so C is equal to Q. Thus, specific heat capacity of a system is defined as the heat absorbed by 1 kilogram of the substance to raise its temperature by 1 Kelvin at a specified temperature. The heat capacity for 1 mole of a substance is called the molar heat capacity. That is defined as the amount of heat absorbed by 1 mole of the substance to raise its temperature by 1 Kelvin. Then unit of heat capacity. The SI unit of heat capacity, molar heat capacity is joules per Kelvin per mole. The molar heat capacities can be expressed either at constant volume, that is CV, or at constant pressure, that is CP. According to the first law of thermodynamics, U is equal to Q plus W, or U is equal to Q minus P delta V, and Q is equal to U plus P delta V. Differentiate with respect to the temperature at constant volume, that is at dV is equal to 0, then you will get dou Q by dou T at constant volume is equal to dou U by dou T at constant volume. Therefore, CV is equal to delta dou U by dou T at constant volume. Thus, the heat capacity at the constant volume CV is defined as the rate of change of the internal energy with respect to the temperature at constant volume. Similarly, the molar heat capacity at constant pressure Cp, that is defined as the heat capacity, the rate of the change of the enthalpy or heat capacity with respect to temperature at the constant pressure is given as Cp is equal to dou H by dou T at constant pressure. Then the relation between Cp and Cv, this will come under 3 mark question. From the definition of enthalpy, H is equal to U plus Pv. For 1 mole of an ideal gas, PV is equal to nRT. By substituting this value, that is the P value in that formula, then you will get H is equal to U plus nRT because PV is equal to nRT. Differentiating the above equation with respect to T, that is dou H by dou T is equal to dou U by dou T plus nR because both of them are constant, so we can take it out. We cannot differentiate it. Dou T by dou T. So dou T by dou T becomes 1. Therefore, dou H by dou T is Cp and dou U by dou T is Cv. So Cp is equal to Cv plus nR. Otherwise, Cp minus Cv is equal to nR. At constant pressure process, a system has to do work against the surroundings. Hence, the system would require a given temperature raised than at constant volume. So, Cp is always greater than Cv. Calculation of delta U and delta H. Here, delta U is the internal energy and delta H is the enthalpy. For 1 mole of an ideal gas, we have the formula Cv is equal to du by dt or du is equal to Cv dt. For a finite change, we have delta U is equal to Cv delta G delta T or delta U is equal to Cv into T2 minus T1. And for n mole of the ideal gas, we get delta U is equal to NCV T2 minus T1. Similarly, for n moles of an ideal gas, we get delta H is equal to NCP T2 minus T1. Based on that, you have one problem. Calculate the value of delta U, that is internal energy change, and delta H enthalpy change on heating 128 gram of oxygen from 0 to 100 degrees centigrade. Cv and Cp on an average are 21 and 29 joules per mole per Kelvin. The difference is 8 joules per mole per Kelvin, which is approximately equal to R. So, coming to the solution, we know the formula delta U is equal to NCV T2 minus T1 and delta H is equal to NCP T2 minus T1. Hence, N is equal to 128 by 32, which is equal to 4 moles. This 128 and 32 is getting from this equation, that is from the oxygen. On heating oxygen, it is given as oxygen. So, the value of that oxygen. T2 is equal to 100 degrees centigrade. C is equal to 373 Kelvin. T1 is equal to 0 degrees centigrade, which is equal to 273 Kelvin. And delta U is equal to, according to the formula, NCV T2 minus T1. If you are substituting those values in this delta U formula, delta U is equal to 4 into 21 into 373 minus 273, that is nothing but 100. And if you are multiplying 4 into 21, we will get 84. Therefore, delta U value is 8400 joules, otherwise 8.4 kilojoules. Then delta H value is equal to NCP into T2 minus T1. And Cp is nothing but 29. If you are substituting this value here, you will get 4 into 29, 373 minus 273. So, the delta H value is 11,600 joules, otherwise 11.6 joules. Like the same, you need to calculate one more, that is evaluate yourself is given. Try this one with the same formula, using the above same formula. Next, we will see the measurement of delta U and delta H using calorimetry. Calorimeter is used for measuring the amount of heat change in a chemical or a physical process. In calorimetry, the temperature change in the process is measured, which is directly proportional to the heat capacity. By using the expression C is equal to Q divided by M into delta V, we can calculate the amount of heat change in the process. Calorimetric measurements are made under two different conditions. One is at constant volume, that is QV, and another one is at constant pressure, that is QP. Delta U measurement. For a chemical reaction, heat evolved at constant volume is measured by using a instrument which is called as bomb calorimeter. The inner vessel, the bomb, and its cover is made of strong steel. The cover is fitted tightly to the vessel by means of a metal lid and screws. A weighed amount of the substance, and here the construction is given. This electrical wires for striking an arc instantly to kindle the combustion. The bomb is then tightly closed and pressurized with excess oxygen. The bomb is immersed in water in the inner volume of the calorimeter. A stirrer is placed in the place between the wall of the calorimeter and the bomb so that the water can be stirred uniformly. The reaction is started by striking the substance through a electrical heating. A known amount of combustible substance is burnt in oxygen in the bomb. Heat evolved during the reaction is absorbed by the calorimeter as well as the water in which the bomb is immersed. The change in the temperature is measured using the Beckmann's thermometer. Since the bomb is sealed, its volume does not change, and hence the heat measurement is equal to the heat of combustion at constant volume, that is nothing but delta UC. The amount of heat produced in the reaction, the delta UC, is equal to the sum of the heat absorbed by the calorimeter and water. Heat absorbed by the calorimeter Q1 is equal to K into delta T. Here K is the calorimeter constant equal to MC. And MC into Cc, and MC is the volume of the calorimeter, Cc is the heat capacity of the calorimeter. Heat absorbed by the water is equal to Q2 into MW and CW into delta T, where MW is the molar mass of the water. CW is molar heat capacity of water, that is a constant value, that is 4.184 kilojoules per Kelvin per mole. By using the equation delta UC is equal to Q1 plus Q2, then you will get K into delta T plus MW CW delta T. K plus MW CW into delta T, because delta T is the common term for both. Calorimeter constant can be measured by burning a known mass of a standard sample. For example, we are taking the benzoic acid, for which the heat of combustion is known as minus 3227 kilojoules per mole. The enthalpy of combustion at constant pressure of the substance is calculated from the equation delta H naught C at constant pressure is equal to delta U naught C at constant volume plus delta mg RT. Then applications. Applications of the bomb calorimeter. This will come under 3 mark question. Mark it as. Bomb calorimeter is used to determine the amount of heat released in the combustion system. Next one, it is used to determine the calorific value of the food. Whatever we are taking, the food calorific value we can determine by the use of this bomb calorimeter. And bomb calorimeter is used in many industries such as metabolic study, food processing, and explosive testing, etc. Next is delta H measurement. Heat change at constant pressure, that is the atmospheric pressure, can be measured using a coffee cup calorimeter. A schematic representation of a coffee cup calorimeter is given in this picture, which is given in the next column. Instead of a bomb, the styrofoam cup, we are taking a foam cup, which is usually given in those functions and all, that is used in this as a calorimeter. It acts as a good adiabatic wall. Adiabatic means there will not be any heat change. This entire heat energy is absorbed by water inside the cup. This method can be used for the reaction where there is no change, no appreciable change in volume. The change in the temperature of the water is measured and is used to calculate the amount of heat that has been absorbed or evolved in the reaction using the expression Q is equal to mW into Cw into delta T. Here, mW is the molar mass of the water and Cw is the molar heat capacity of the water, that is a constant value. That value is 4184 kilojoules per Kelvin. Next, one problem is given here. Calculate the enthalpy combustion of ethylene, that is C2H4, at 300 Kelvin at constant pressure. If it's a heat of combustion at constant volume, delta U is minus 1406 kilojoules. The complete ethylene combustion reaction is given here as C2H4 plus 3 oxygen gives CO2 plus 2 water molecules, 2 CO2 and 2 H2O. The delta U value is given as minus 1406 kilojoules. Delta N is nothing but the difference between the number of products minus the difference between the number of reactants. Here the products is 2 carbon dioxide and 2 water, and the reactant are 1 ethylene and 3 molecules of water. But here we are not considering water because it is in the liquid form. So 2 minus 4, which is equal to minus 2. Delta H is equal to delta H plus RT delta N G. Here G is mentioned as number of molecules difference in the gaseous state. That's what we are not considering the water because it is present in the liquid form. And delta H value, if you are substituting those values, minus 1406 plus 8.314, that is the value of R into 10 power minus 3 into 300, that is the temperature in Kelvin, into minus 2, that's the difference in the number of moles. If you are multiplying, and you will get minus 1410.9 kilojoules. Like the same, one more evaluate yourself is given. You try this one in your chemistry notebook and find out what answer you are getting. Then application of heat of combustion. Calculation of heat of formation. Since the heat of combustion of organic compounds can be determined with a considerable case, they are employed to calculate the heat of formation of other compounds. For example, let us calculate the standard enthalpy of formation of delta H naught F of methane from the values of enthalpy of combustion for hydrogen and C, that is graphite, and methane, which are minus 285.8, minus 393.5 and minus 890.4 kilojoules per mole respectively. Now let us interpret the formation of the about the enthalpy of formation by writing out the equations. It is important to note that the standard enthalpy of formation of pure elemental gases and elements are assumed to be 0. The element as well as some gases are there. Their heat of enthalpy of formation is 0 using the standard condition. So the thermochemical equation for the formation of methane from the constituent element is given here. C, that is graphite in the solid state, plus 2H2 gives CH4. Here the delta H formation we are going to calculate, so we consider that one as X kilojoules per mole. Thermochemical equation for the combustion of a given substance are H2 gas plus half O2 gives H2O liquid, and its formation value is minus 285.8 kilojoules per mole, and graphite plus oxygen gives CO2. Its standard enthalpy value is minus 393.5 kilojoules per mole, and methane combustion reaction gives carbon dioxide and water. Its enthalpy changes minus 890.4 kilojoules per mole. Since methane is in the product side, the required equation we have to reverse. Okay, that is the product is converted into the reactant and the reactant is converted into the product. So CO2 plus 2H2O gives CH4 plus 2O2. In order to get equation from the remaining, equation 1 from the remaining, 1 is equal to 2 into 2 plus the third equation plus the fifth equation. So x is equal to, if you are substituting those values, then you will get x is equal to minus 285.8 into 2 plus minus 393.5 plus 890.4. If you are calculating and you are substituting those values, you will get minus 74.7 kilojoules. Hence, the amount of energy required for the formation of 1 mole of ethane is minus 74.7 kilojoules. The heat of formation of the methane gases minus 74.7 kilojoules per mole. Calculation of the calorific value and food values. Calorific value, this comes under 2 mark question. The calorific value is defined as the amount of heat produced in calories or in joules when 1 gram of the substance is completely burnt. The SI unit of the calorific value is joules per kilogram. However, it is usually expressed in calories per gram. Heat of solution. Heat changes are usually observed when a substance is dissolved in a solvent. The heat of solution is defined as the change in the enthalpy of 1 mole of the substance is dissolved in a specified quantity of water at a given temperature. Then heat of neutralization. The change of neutralization is defined as the change in the enthalpy when 1 gram equivalent of an acid is completely neutralized by 1 gram equivalent of the base, or vice versa. Vice versa means 1 gram equivalent of the base is completely neutralized by 1 gram equivalent of an acid. That is in the dilute solution. For example, HCl in aqueous solution plus NaOH in aqueous, you will get NaCl in aqueous and H2O water. The delta H value is minus 57.32. Here the equation, ionic equation is H plus OH gives H2O and the delta H value is the same, that is minus 57.32 kilojoules. The heat of neutralization of a strong acid and a strong base is around the same value, that is minus 57.32 kilojoules, irrespective of the nature of the acid or base used, which is evident from the below equation. That is, if you are taking the HCl and KOH, you will get HCl and water, and if you are taking HNO3, that is nitric acid and KOH, you will get KNO3 and H2O, and sulfuric acid also converted with the KOH, it is converted to K2SO4 and water. So for all the reaction, the delta H value is minus 57.32 kilojoules. The reason for this can be explained on the basis of Arrhenius theory of acids and bases, which states that strong acid and strong bases are completely ionized in the aqueous solution to produce H plus and OH minus ion respectively. Therefore, in all the above mentioned reactions, the neutralization can be given as H plus and OH minus gives H2O water. Therefore, the delta H value comes as constant. Molar heat of fusion. The molar heat of fusion is defined as the change in the enthalpy when 1 mole of a solid substance is converted into liquid state at its melting point. And for example, the heat of fusion of ice can be represented as H2O gas at 273 Kelvin gives H2OL, and the delta H value of fusion is plus 5.98 kilojoules. Molar heat of vaporization. The molar heat of vaporization is defined as the change in the enthalpy when 1 mole of a liquid is converted into vapor state at its boiling point. For example, the heat of vaporization of water can be represented as water liquid form 373 Kelvin. It is converted to water vapor. the delta H value is 40 plus 626 kilojoules. Then molar heat of sublimation. Sublimation is a process when a solid is changed directly into vapor state without changing into liquid state. So the molar heat of sublimation is defined as the change in enthalpy when 1 mole of a solid is directly converted into vapor state at its sublimation temperature. For example, the heat of sublimation of iodine is represented as iodine solid at 373 Kelvin iodine vapors, and the delta H value is plus 62.42 kilojoules. Another example of sublimation process is solid carbon dioxide to a gas at atmospheric pressure at very low temperature. Next, heat of transition. The heat of transition is defined as the change in enthalpy of when 1 mole of an element changes from one of its allotropic form to the another form. For example, the transition of a diamond into graphite. Both diamond as well as graphite are carbon in its allotropic form. The C diamond is converted to C graphite. The enthalpy needed for this one is plus 13.81 kilojoules. Similarly, allotropic transition in a sulfur and phosphorus can be represented as S monoclinic is converted into S rhombic sulfur, and in phosphorus this is P white, that is white phosphorus is converted into red phosphorus. Their delta H values are, for sulfur it is minus 0.069 kilojoules and 67 kilojoules, and for phosphorus it is delta H transition, that value is minus 4.301 kilojoules. And the next one, you are going to pass on one more important law, that is Hess's law of heat summation. We have already seen that the heat changes in the chemical reactions are equal to the differences in the internal energy, that is delta U, or the heat constant, that is delta H, of the product and reactant, depending upon whether the reaction is studied at constant volume or at constant pressure. Since delta U and delta H are functions of the state of the system, the heat evolved or absorbed in a given reaction depends only on the initial state and the final state of the system, and not on the path or the steps by which the changes takes place. So, the Hess's law is stated as the enthalpy change of a reaction either at constant volume or at constant pressure is the same, whether it takes place in a single step or a multiple steps, provided the initial and the final states are the same. For example, A is converted to X. It is directly may be converted A to X. Otherwise, first A is converted to B and B is converted to Y, and again this X is converted to Y. Like that, it may be takes in the 3 steps also. So, the delta H reaction is equal to delta H1 plus delta H2 plus delta H3. And its application. Hess's law can be applied to calculate the enthalpies of the reactions that are difficult to measure. For example, it is very difficult to measure the heat of combustion of graphite to give pure carbon monoxide. However, the enthalpy for the oxidation of graphite to carbon dioxide and carbon monoxide to carbon dioxide can be easily measured. For these conversions, the heat of formation values are minus 393.5 kilojoules and minus 283.5 kilojoules respectively. From these data, the enthalpy of the combustion of graphite to carbon monoxide can be calculated by using the Hess's law. The reaction is C graphite is converted to carbon monoxide, and that is the one step with a half oxygen molecule, and graphite is converted to carbon dioxide, and again this is a reactor, and with carbon monoxide again with half a molecule of oxygen that is converted to carbon monoxide. So according to Hess's law, delta H1 is equal to delta H2 plus delta H3. So that is minus 393.5 kilojoules, which is equal to X minus 283.5 kilojoules. Therefore, X value is minus 110.5 kilojoules. Okay. So with that, I finish this part of that lesson, and the remaining lessons we will see in our next class. Okay. And in this one, I am giving you the PDF form of the question and answer. Take down all those question and answer in your class or notebook. Okay. Thank you, children.